Here is an example that requires the use of the full Newtonian gravitational potential energy. See if we can set something up here. We're going to have time initial, time final. Let's consider the Earth and a small object some distance from the Earth. In fact, we'll let this distance be about 10 to the 12 meters. And it has a mass m. Here we have the mass of the Earth. And we'll suppose that it's starting at rest. So the V initial is going to be 0. And the 10 to the 12, that's going to be the R initial. But now let's consider the speed of the object when it's fallen a certain distance. We can squeeze it all in here. Mass of the Earth. Now, well, since it's starting at rest, it's going to fall straight down to the Earth. So the object has gotten closer. It's now moving at least a little bit faster. The V final is what we want to find. Maybe in the math we'll just call it V. We'll see about that. And let's suppose that the new distance is 10 to the 10 meters. So that's going to be the R final. We can develop this like before. Instead of just grabbing the equation, we could step back through it again very quickly. We know that the mechanical energy initial is going to equal the mechanical energy final. Mechanical energy is coming from the kinetic energy of the object. So the kinetic energy initial and kinetic energy final. And then we're going to add in the gravitational potential energy, initial and final values. Now we can substitute in what these energies are. With the kinetic, we have 1/2 mv initial squared. The potential energy has that negative sign, so we'll bring it out as a subtraction, and it's minus g, the mass of the Earth, the mass of the object divided by the R initial, and then we'll have the same expression except with the final values. And once again, the mass of the small object, not given in the problem, is a factor in each term, and we can actually divide it out. It cancels out of the equation. So the mass of the object in free fall still is irrelevant. And then we're going to have a new equation, and we can plug in some numbers here. The V initial is 0, and the V final we're just calling F. The other values, well, we can look up the mass of the Earth. We'll see. I'll try to put something in there. So we have 1/2. The V initial is 0 squared minus, the G as well. That's 6.67 times 10 to the negative 11 in SI units. And then it's times the mass of the Earth. That's 5.98 times 10 to the 24 kilograms. Divided by the R initial, which I believe is 10 to the 12 meters. And this is going to equal 1/2 times the final speed squared. We're just calling that V. So V squared and minus 6.67 times 10 to the negative 11 times the mass of the Earth once again, 5.98 times 10 to the 24, and divided by the R final, which is 10 to the 10. So where the equation is coming from is pretty straightforward, but once you plug in the values, especially the rather unattractive scientific notation numbers, may not be quite so obvious what to do with this. I'm going to take it, or at least you can look at it and say, wow, what a pain. I'm going to rearrange a little bit. Have the 1/2 v squared on one side. On the other side, of course, that 0 part just disappears. We don't need that. We can take this entire expression to the other side where it becomes a positive. So we're going to have the 1/2 v squared equals 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 10 to the 10 and minus the 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by the 10 to the 12. And of course we can put this into the calculator at any time. I'm just kind of trying to show something maybe a little bit better, plug everything in at once. If we look at the expression on the right, we can actually factor out a good bit of this. The 6.67 times 10 to the negative 11 can factor out. The 5.98 times 10 to the 24 will factor out, and we're left with 1 divided by 10 to the 10 minus 1 divided by 10 to the 12. So the expression's still a little bit ugly looking, but maybe easier to deal with now. For solving for the v, well, I'm going to multiply both sides by 2. So I'm going to have 2 times this full expression once again. I'm going to give it a try. Copying and pasting would have been a little bit easier. That was multiplying both sides of the previous equation by 2 to get rid of the 1/2. And then that's going to leave the v squared. So the v itself, being a positive number, is going to be the positive square root of this entire expression. And again, you don't have to do it this way. You can write down intermediate results, but this is one kind of appeals to me. To wait to the very end, plug everything in, and get a result out. And someone checked me on this. I think I got 281.0 meters per second. But if anyone disagrees with that, it's always possible I put something wrong in the calculator. Just let me know. Certainly hope that it's good enough. In any case, there's one example of making use of the full-blown Newtonian gravitational potential energy formula. Whew!